microphone works, you can hear me? All right. For all of you who want to take notes, you better listen because I have a lot of slides. I'm going to go fast and, better going to look at the slides. There's a lot of content. Let's see. I'm a Lucene core committer. I'm the PMC chair right now. I took over from Grant last year. I'm a co-founder of Building Buzzwords, and I co-founded Searchworking, searchworkings.org, which is a community portal around Lucene, basically around open source search and all the related stuff. So if you're interested in that kind of thing, go check it out. But I don't want to talk too much about Searchworkings today. I want to talk about the challenges we've been facing in the last couple of years. I try to make it from all kinds of perspectives. User perspective, developer's perspective, technical things, community things, environmental things in terms of our programming language. And it was super hard to find or to make a selection of the problems I'm going to present today because we had so many challenges. We solved most of them pretty well. So, yeah, some of them you might have seen before in various presentations. There's a little bit of an overlap between what Mike and Robert did yesterday and some overlap over things I've been doing in the past. But yeah, let's see. If you have any questions, try to keep them for you until the end of the presentation. Since, well, I said I have a lot of slides, but I've already got through 4 in 58 seconds, so it's pretty good. Okay, a little bit of history. Apache Lucene has been a top-level project since almost 2001. I think it's 2001. And it's been creating other projects a lot of people you use, been creating like things like Nudge, Hadoop, Mahout, Tika, right? Almost everybody knows. If you use Solar, or if you use anything in a bigger scale, you probably touch some of them too. So Lucene has always been a playground for new big things in the Apache Foundation. I personally only work on Lucene. I don't focus too much on Solar because there's just so much work to do there. So this presentation is rather not about Solar. So some of the things might apply to it, but it's basically from my Lucene core committer perspective. Okay. The most important thing on this slide is, and I want you all to remember this, Lucene has been developed and it's maintained by volunteers. Some of us get paid for doing the work, but all of us only do the work because they really, really like it, right? It's a very passion-driven software, I would say. And if you follow the dev list here and there, you probably realize that there's a lot of passion involved one day or another. Okay, this thing doesn't work. Go this way. Okay, so I've been given this presentation once before, and people were asking me, so it's a search engine, so what's the big deal? It's like, yeah, it's just software, right? But with all the passion involved, we want to make this thing fast, reliable, cool, and we want to make it that the most of the people on this planet are going to use this, right? We want to have everybody using Lucene. We don't want to force it, but if it's good enough, it's going to happen. So Lucene has been mission critical for a lot of companies, and I think the most of you here, a big portion of the infrastructure is basically built on Lucene, or at least something which is important in the application, whatever you do, right? In contrast to any vendor, right, anybody who sells software, we don't have any contracts. We don't. You're not going to download and you sign up for something, and if it breaks, you're going to call us and say, dude, this sucks, right? You need to fix this. The only contract we have is trust. You have to trust the community. You have to trust the software. When you download it, you install it on a computer. You run your, as I said, mission-critical application on top of it, and it fails. Well, you need to deal with it. There's no Microsoft you can call and say, I signed this contract, you're going to show up here tomorrow and fix it. So that's actually something pretty big on the shoulders of all the committers. It's not like that we feel it every day, but it's certainly there. Today, we're roughly about 30 committers. Maybe I'm wrong. Maybe there are even more. We added a lot of people in the last 4 months. We kind of changed our way of how we get committers in. Previously, it was more like that you had to be more of an I know all parts of Lucene guy. These days, this is kind of different. We have more committers. They basically focus on one part. They can commit to everything. And they're always happy to create patches. But this kind of perspective has changed for us. The software has been getting bigger. There's more code to maintain. So we added more committers for smaller things. Which doesn't mean that committers are like more of a committer or less of a committer. So we all basically the same. I wonder if you realize that we don't have anything like a tech lead or somebody who makes the decisions. If there's some arguments or there's no no daily stand-ups kind of things. We don't call each other on a daily basis. It's all driven on Jira and the mailing list. All this IRC, depending on the discussion, if you can keep up with the speed of people discussing things, then it's kind of fun to watch. But except of this, we do everything over written communication. And the thing in the Apache Foundation is it should all be public too. We had a couple of arguments in the past that, if you have a private chat with one of the committers because we know each other, is that correct or should we do it differently? I would say 95% of the communication goes over public mailing lists. Hopefully that's true. Don't nail me down in this. So as I said, we don't have any tech lead, so we have to somehow agree on a change, right? So consensus is king usually. There's a lot of arguments, a lot of passion involved, which very often means that there's sometimes, there's a -1 coming in. -1 basically means you can't do this. I'm going to block this. A committer has the power to block a change. It doesn't happen too often, but it happens here and there. We have to figure this out, but usually we get along pretty well. Some people might seem as a kind of a rough tone on a mailing list here and there. It's true, but don't get impressed by this. Just be a little bit rough back, and that's fine. We got a lot of mails, so I was just, I visited Mike McCandless the other day, and one of his kids was saying he gets a lot of emails a day. He was talking about 2 or 3. And Mike was saying, we get there's 10,000 mails a month on this mailing list, so there's a lot of stuff to read. I mean, it's in every company, you get a lot of mails too, well, anyway. All right. So let's talk a little bit about community. Dependencies, right? So yesterday, there's nobody was really talking about this. There was Lucene, it was little Java, it's all good. It had no impact on the community, no impact on dependency. Well, Java is the dependency, right? When we talk about zero dependencies, there's nothing third-party except the Java. Well, this thing kind of changed, right? There's Oracle coming into the picture, Harmony is shutting down. We had some private discussion of continuing with Java is the right thing. It obviously is, so don't worry, we're not going to change this. But I just want to give you the idea of that we have a zero dependency, and we are community driven, but ultimately we depend on Java, right? So this is a big thing also for us, and we think about this too. So none of us knows what's going to happen tomorrow if you have to install a 10G if you want to run Java, right? They're going to force you to do this. Going to suck up 3 of your CPUs. You never know. So we try to make it fast. If that's going to happen, we're going to be still fast. All right, this still doesn't work. All right, community. What are you guys looking for? Well, I figured there's 3 basic things. There's performance, there's innovation, and there's confidence, right? There's API stability. And what that ultimately means is that we need to figure out where we're going to put our software here. I took Lucene 3 here as an example because it's pretty stable in the API. It's pretty performant, but over the last couple of years, it didn't get too much innovation. The reason for this was that, it grew over time. There was 6 years. There were some API changes, some index changes, but nothing major, right? So research going on. A lot of people do research in information retrieval. There's new things coming up. We needed to go and be a little bit more flexible. So this is probably what Lucene 4 is. Lucene 4 is more of the innovation side. It tracks in new users. It tracks in people from the academic side to actually use it, extend it, try new things out, do the research. We were actually not implementing the last couple of years on Lucene, and this is what we also wanted. This is one reason why we came up with all the big changes in Lucene. Performance on the other side, well, sure, right? You don't want to wait 2 seconds for a search request to come back. So it needs to be fast. But it's actually a pretty hard challenge to find the balance here, right? Ultimately, we need to move this a little bit more over here. API stability is currently not what is guaranteed in Lucene 4. Things change every day. And sometimes I had a presentation about doc values last year at the Lucene Revolution. And I changed my slides 5 times in the last week because the API was changing so fast. So we are stabilizing on this, and it's going to be an alpha release sooner or later. Robert was saying in the next couple of weeks, so I'm not believing that yet, but let's see. I've been saying months for so long. I've been saying like, oh, it's going to come in the next couple of months. Yeah. Probably switched to years now. Okay. So let's get a little bit more into what Lucene is. It's essentially a library, right? Everybody who's new to Lucene is going to ask, hey, how are we going to start this up? Well, basically you don't, right? It's if you want to start something up, you use Solr, you use Elasticsearch, you use there's other frameworks like Compass around, or Kata, which is Lucene on top of Hadoop. But basically, all we care of making the core features as performant, as stable, as reliable as possible. All the stuff on top, like how to use this API, is going to happen in Solr or other things. So that's also causes a couple of problems, because most of the users, they don't look behind the scenes. I mean, you look behind the scenes a little bit, but you can't get down the whole stack. This library is so big. If you want to look really behind the scenes, you need to spend, Robert said something like you need to dedicate your life to it if you want to keep up with what's going on there. And that makes a lot of things tricky for us, because we need to make sure that all the pitfalls, all the caveats are actually visible. They're obvious, they're documented, right? You need to make sure people understand what's going on. If a class is thread safe, we had a guy coming in the mailing list asked, hey, is the Lucene class thread safe? And I basically replied to him and said, index writer and index searcher is basically thread safe. And then he came back with this list of packages and asked me, can you go through the packages and tell me which class is not thread safe? Yeah. Yeah, so what can I say, right? It's obviously not obviously enough. So that's a big problem. The data structures are hidden behind the APIs so tightly. You don't even get close to them. Right? But you need to understand them at some point if you want to use them efficiently, or if you run into performance problems. But the only way for us to do this is actually to document the stuff. And this is what one of the still not solved challenges is in Lucene. Like Lucene 4 is going to come out, let's say, I don't know, September 1st. But Lucene in Action 3 is not going to come out September 1st, right? It's not there. The big documentation, I mean, Mike's too lazy to do it, right? But it's not going to be there, right? There's a big piece of documentation missing here. There's so many things changed, and we try to resolve this at some point. There's a lot of ideas, like writing an open source book. Every committer should write a chapter, blah, blah, blah. We can maintain it. Yeah, if you have any ideas or if you want to contribute documentation, this is one of the big unsolved challenges, right? That is where we need more power. Like, how many core committers are there? How many core committers are active? It's like a handful. We do a lot of work. We cannot write a book next to writing the search engine. We need help. So here's my, please, Patch is welcome. If you have ideas, if you're a technical writer, come in, help us. It's great. And the community is great too. If you want to get outside of the community, it's good fun. Okay, let's see. Let's talk about the fun challenges everybody wants to work on, not the writing. Shouldn't have said that. Okay, well, it's written in Java, so it's going to be fast, right? No worries. There's hundreds of different use cases. I mean, Grant plays chess with Lucene, and some other people, you know, they run it on Android. Others do map search. Sonex does his business shop with it. Twitter searches in real time with a heavy modified Lucene version, but still, there's so many different use cases, right? There's one library to rule them all. At least we hope. And there's a lot of surprises in Lucene. One of my favorite examples is the lowercase filter. If you don't know what supplementary characters are, I'll give you like a short intro. It's a Unicode construct where we basically extended the range of Unicode to have more characters in. So that's the short thing. Maybe it's not completely correct, but it's fine for now. I have so many slides. But actually, lowercase filter, it does case folding, right? And there's actually not even a single language that is expressed in supplementary characters or is above the base multilingual plane that has case folding, except of this one script the Mormons use. So we figured, oh, let's stuff that. We just are not going to support it. So what happened 2 days later, somebody came in and it's like, hey, I indexed these 8 books around in the world written in this script. It's like, okay, so probably better going to do it. So there's nothing possible here. And there are bugs. We recently, well, not recently, last year, we ran into a bug which basically has been sitting around in this skip list implementation for almost a decade, right? It's been in there for so long, and it took like 10 years. And the only way to actually figure this out is one of the challenges I'm going to talk about in a couple of minutes, is how we change the test infrastructure to make sure we don't have too many bugs, or the bugs are not so critical. Yeah, essentially it's a mission-critical software shipped for free. Thank you to all the committers. So if you read this, I didn't state if it's true or not true, so, right? Wait until the next couple of slides. It's actually, most of them are not true. So don't like copy this, go to your boss and say, look, we can use JDK collections, they're going to be freaking fast. No. So there's a couple of things, since we are in Java, we need to take care of. So there's tons more, but those are the most prominent ones, I would say, and causing a lot of problems, especially those kind of things here. The JIT compiler. It's an awesome piece of software. It's so good in optimizing things at runtime a static compiler can't do, but there's a lot of stuff hidden in a black box. The JIT compiler for us is also a black box, right? We can go off and say, and we look at the compile assembly, but that doesn't really give you an idea what's going to happen in production, because the JIT compiler could make a different decision back then. You could go in and say, oh, look, this function call is going to be inline. Awesome, no problem. You're going to load another 2 instances of this interface, and it's not going to be inline anymore. But it's totally tricky. It's implementation dependent, or you have different JVM. You have different characteristics. But yeah, since I want to talk about challenges and give you a little bit of an idea how we work, I'm going to look into those kind of things here to give you an idea how we do that. If you're not so much into Java, so it might be a little bit boring the next couple of slides, but you know, it's going to be better in like 5 or 6 of them. So here's my statement. No. Right? It's not. And one of the biggest things I learned in the last couple of years is that you have to have some kind of sympathy to the environment you work in. There's a Formula One racer guy who his name is Jackie Stewart, right? And he won the Formula One championship in 1967 or something. And he said, like, to win the Formula One championship, you have to have mechanical sympathy. You need to know how your car works, right? You need to feel that it's not tuned right. And you basically need to know what's going on. And this quote here is one of my favorites. Like, we spending so much time in making, killing what the hardware industry does with software, it's not even funny. Right? A single CPU can do so much if you do it right these days. And people say, you need multi-core, and they're all going to be faster, and you don't worry, you're just going to spawn your threads, and you'll be fine. It's not true. You still need to think about what you're doing. That's my statement I want to give to everybody. Like, next time you write your software and it needs to be fast, you should really think what's going on down there to make it that fast. Anybody disagreeing? Good. All right. So what do we focus on? And that's probably a little bit influenced by me, myself. But what I focus on is other people who focus on different things, but that's from my perspective. The biggest things when we write software for Lucene is do we have like a good utilization of resources? Do we impact the garbage collector? Do we use the right compression? Can we make it smaller? Robert is one of the guys who made like the Kumoji dictionary so much smaller, where a lot of people are thinking like, that's impossible to compress even more, and he got another couple of megabytes at it. So that's really important that you get your first level of compression. Don't stop. Look one more time. There's probably a little bit more to compress there. Concurrency is my favorite, so I'm not going to talk about this too much if we get excited. But those kind of things this little map here is something. If you want to write something which needs to be really fast, look at this slide and think about, like, do I use concurrency efficiently? That doesn't mean like you have to use it, right? Sometimes concurrency doesn't do good. Do you have a big impact on garbage collection? Do you create a lot of objects? Short-living objects are not for free, right? That's a myth that's been coming up in the last couple of years. If you create a ton of them, like 100 million, they're not for free anymore, right? You need to run through this in the garbage collection step. So basically, those should give you like a little idea when you want to patch something in Lucene. Just keep that in mind. You don't need to go like it's not a list you need to do, but that's probably a good first step to see what you can optimize. And those are the more specific things what we focus on, like efficiently exploit file system OS caches. A lot of people ask us, what's the memory requirement for Lucene? General answer is as much as you can give it, right? But not the JVM. To give memory to Lucene doesn't mean you have to give like 10 gigabytes of heap space to the JVM. I recently wrote a prototype which performed super well with a 20 gigabytes index and 40 million documents in it, and it was like I started it with the default settings of the JVM, right? No additional heap, and there is no big garbage collections going on. Lucene is very efficient on that level, but we try to exploit these kind of things and make sure we don't have to deal with the memory here. So we just leave it to the OS smart anyway. Right, I can't go through all of them, but it should give you an idea that when we work on stuff like, file formats or fuzzy query or the automatons, index writer, index reader, those are the kind of things we try really to focus on. So making things fast and stable is an engineering effort. It takes time. It takes a lot of time. Go tell your boss. Right? Even if it comes in the next time and says, this needs to be fast tomorrow, you probably can tell him it's probably not going to be fast tomorrow, but it's going to be faster than fast next week. Maybe that's a good argument. So he'll come back and say, is this all necessary? Yes and no. There's certainly parts where optimization are totally premature. They're completely not giving you any performance hit eventually. But it really depends on if you figure out what the right hotspots are. And that's probably one of the biggest things we try to make sure that we find the hotspots in the software and go and optimize those. Some people tend to first optimize and then figure out that the performance test was actually off by 1,000 times. So yeah, make sure that you test. You really need to test, and you make sure that your test's right. And we were just talking about it. It's so funny. We had Robert was working on the suggester, and he was like so worried because he was coming back with 50 queries per second, and he wanted to add a new feature, and he was coming back with 45 or something, and he was like worried that he cannot add the feature, but it turned out that the performance test was actually off by 1,000, so it was actually 50,000 queries per second. So, but we optimized the shit out of it. So you really need to make sure that this is going to be fine. You know what you're optimizing. Okay. One thing I wanted to give you up is then that actually Java doesn't really optimize everything. Java iterator is a good example of how not to design software, in my opinion. You know, like just to iterate over a list, do 2 function calls, it probably doesn't really matter. If you iterate over 10,000 objects, if you iterate over 52 million objects, it probably makes a difference, right? So you can probably think about this ahead of time. But yeah, don't want to give you any lessons here. Let's look at the concrete problems. The challenges. When I started this presentation, when I preparing the presentation, I had 15. So I cut it down to 4 because after, you know, even like I looked at how many slides do I have after like putting 15 slides in just to have 1 slide per challenge. And eventually it turned out that 1 challenge was like 10 slides, so 15 would have been a little bit too much. I cut it down. Anyway, yeah. The first one I'm going to talk about is I call idles not good. That is related to the index writer. One data structure to rule them all. That is more or less related to the codec stuff we've been done in Lucene 4. How to test the library. I referred to this a little bit previously where I was saying like how to figure out bugs which have been sitting in there for 10 years. Right? They're not going to just show up in your unit test unless you change something. My favorite one, and I have a couple of funny pictures there too, so you definitely need to wait for this. Even if Eric tells me that I don't have enough time. What is needed for a 20,000% performance improvement? Okay, let's go. Everybody who is using Lucene to build an index and wants to push a lot of objects in there, a lot of documents, might have realized that it's a pretty I/O and CPU-intensive task. So if your document's not super, super small, and then you're probably going to run into like big merges, you're going to run into slow commits, slow flushes in the past. But when I say slow, you know, it's a pretty high level. The Lucene index writer was really fast before. It wasn't that you know you could go and get coffee when you index 3 documents. It was really, really, really slow, really fast actually. But it wasn't that fast. It wasn't as fast as it could go. We haven't had the problem actually that we needed to think about making it faster. We had the problem that somebody was coming in and said he wants to do something different with the index writer related to real-time search, and that started this whole refactoring. And that's actually when we realized that we can make this thing way much faster. What I have to tell myself all the time, especially when it gets to concurrency, is don't get crazy, right? You can make code extremely complex so that nobody else can maintain it anymore. So that's also a big discussion we usually have, but it doesn't really apply to this particular issue. Well, some pieces of code. Anyway, the ultimate goal for us was to scale up the CPUs as well as the I/O saturation of your computer to make it really busy, so you can't run any databases on it anymore. To make sure, you know, like Larry comes in and says 10G, you know, I don't know. Okay, so here's the problem: indexing Lucene 3. So that's what I index here is the Lucene, the Wikipedia dump English. It's about 7 million documents. The index size is going to be 20 gigabytes roughly. And what you see here is a slice out of the window of the indexing documents per second during one of these sessions. And you see that like after 80 seconds, it suddenly drops. Nothing gonna happen anymore. But that's right, like there's no documents coming in. No, what's gonna happen there? I don't know. Indexing was still pretty fast, so 620 seconds for 7 million documents, not bad. Right? You can live with this, that's fine. I have to admit it's a pretty big box. Some of the committers have pretty big workstations. We call them beasts. And yeah, try to run more tests and get more bugs out of concurrency, having more CPUs, et cetera, et cetera. Anyway, so what actually happens here is that if you look at the index writer, how it worked internally is that you had a couple of thread states, so indexing threads coming in, get a thread state assigned, index into a small in-memory segment, and once the famous max RAM buffer fills up, it flushes stuff to disk. But before that, that stuff gets merged into one segment and then written to disk. And this process here, this single-threaded sequential process where all the indexing threads need to stop, that's what you see here. And it's a pretty big time slice, right? It's actually more of the time than we actually can index. It also turned out that this whole process here, code-wise, was extremely complex. There was so many classes, so many calling back and forth from one thread to another, that we were actually able to make this faster and simpler. It's even better. So what we did is we made it super simple, right? There's no merging anymore down there. We're just going to write it to disk and pay the price of doing on-disk merges. But it actually turned out to be faster than doing that in memory. The outcome of this is this graph. And you'll probably see and recognize these little spikes here where it goes down. I was totally puzzled. When I saw this the first time, I was totally puzzled. What is causing this? Like garbage collections, there's contented locks could be the reason. Actually, the reason was that I was reading the documents from the same hard disk, and my computer is so busy that it couldn't even read anymore from the hard disk. So this is what I mean by making your computer as busy as possible. You can't run a database on it anymore. Indexing became a lot faster, but it also became a little bit more complex in way of how you tune it. I can only recommend you, if you have done something in Lucene 3 with indexing, try to optimize it for performance. It's going to be harder in Lucene 4 to find the right settings. But a general advice is, give it less memory as you give it today, and give it more threads as you give it today. More threads, less memory, that's the price. That's what you can remember as a rule of thumb. It usually should give you something between 250 and 300% indexing improvements. Right, okay. The next challenge, one data structure to rule them all. Well, there was one index in Lucene, one index format. There was basically no way to change how we write postings, how we write the term dictionary, what kind of data structures we use in there, what price you want to pay, what kind of documents you have. Like Twitter has this 140 characters and doesn't have a lot of positions, so we probably could inline that in the posting lists. When you wanted to do something like this, you basically had to take the source, modify it, and make sure that no committer is going to break your change over time. Not a really good idea in the first place, and probably a lot work intensive. Okay. Back to the research I was talking about before. There's a lot of things where people were researching in the integer compression, inlining stuff into posting lists, like the pulsing codec we have today for unique IDs, and holding the posting list pointers, preventing this not going a second in direction to disk. So somebody came up, and I think it was in Duck like 6 years ago, where the first draft of flexible indexing came out, and a couple of people brainstormed. It was like Grant Ingersoll was involved in this. It took about 6 years to get there. And it's kind of funny that Mark Miller mentioned the other day that, we are there already. We were talking about this yesterday, and we're there now. It's kind of really, really nice that we eventually fixed this challenge that you can plug in your own index, basically, underneath Lucene. Okay. This is what, I got 5 minutes left, so I'm going to speed up a little bit. Okay, so this is what we had in Lucene 3. Basically, there was no level between the directory and the file system. What we have now is basically a level in between, right? We have the Flex API, index reader and index writer. They use this Flex API, and underneath there's a codec which takes care of encoding all the data structures underneath. So you can change it. All right. One reason why we did this is, or maybe it was not a reason, but it's a nice side effect, is that we can now freely change, in every upcoming version, we can freely change the index format. Because the codec is actually something which is per segment. So if you have an old segment in the index from Lucene 3, and you're going to use Lucene 4, it's magically merging that stuff behind the scenes. I'm going to upgrade your index on the fly. And if we're going to change something like moving one bit to another position in the index in Lucene 5, no worries, you could just upgrade. And we have the freedom to do this. It also gave us the right tool for the job. Like, switching to memory postings gave a tremendous speed up. This is what Mike was referring to this, it was 2 times. But what he wasn't saying is that it came from 200,000 lookups per second up to 550,000, right? So 2 times, if you have 2 queries per second, it's not that impressive. Here, it's pretty much very impressive, I would say. Same is true when we added a new index term dictionary for the fuzzy queries. It speed ups the stuff dramatically. It's just changing the data structure. I mean, right? It's a lot of work, but it can do magic things. That layer gave us so much freedom. It was a challenge before it was a solved challenge, or it was a challenge, but we didn't even know about it at the point where we implemented it. Okay, let me really, really quickly go through this. And then I want to show you the funny pictures. Not all of them. Okay, how do we test the library? Recently, 1.5 years ago, we switched to random testing, right? Every test gets a random seed, selects random parameters for all kinds of things, random configurations, random merge policies, random codecs, random everything, random Unicode strings. Broke about every JVM on this planet. They were all just crashing on us. Yeah, it solved one of the biggest challenges ever. Like, you have continuous integration, you run tests, and you run it over and over again without a change. It's just a waste of CPU cycles, right? Back to the utilization challenges. All right. This is the thing. 1 run equals 1,000 runs. What's the point? There's no point of doing this, right? There's no point of running this when you didn't change anything. And you don't change too often, so your computer is idling, and idle's not good. All right, when you basically look at this test case here, it's very, very simple, right? It uses math.apps for a random integer, and well, it basically tests if the buckets are right. Can this test fail? It passed, right? How can this test fail? Look at the upper one here. The problem is up here in the second line of this method. It actually can fail, but it took 51,139 runs to fail. And it failed, why? Well, because there is no positive representation of integer min, right? So you can run math.apps on integer.min value, and you're not going to get a positive value back. That's a simple thing, but we can actually do that in a big scale. We did that for all of the scene. It was a lot of work. It took really long time, but eventually it showed up so many errors and so many problems. We were able to fix so many things to reduce the number of bugs, to make the user happy. And if you are interested in that kind of stuff, I have this on the next slide. There's We extracted this, David Weiss did that. You can download it. The infrastructure for random testing is there. And there's a couple of presentations. If you search for random testing and David Weiss, you'll find that stuff. Okay, I'm close to the picture. Here it is. What do you need for 20,000% performance improvement? Well, it's coffee, fun, and beer. And that's my message for today, right? If you want to have fun with Lucene, if you want to write something cool, coffee, fun, and beer is what you need. My last slide, I'm going to skip a couple of them. Here, that's the one. Who we are, who builds Lucene. It's not a single guy, it's a true team effort. So many people who's dedicated a lot of time into this project. Nobody knows all of it. There's no creator of Lucene. It's like Martijn, Robert, Uwe, Mike, there's Eric Hatcher sitting here, Eric Ericsson's here. Every committer I forgot. It's like there's David Smiley here. Christian. Thank you guys, and thank you.